All right, there's a number on the board. If you please go ahead and text me at that number. In the text, you want to make sure you write logic control, and then you want to put your first name and last name, and that'll be for attendance. So if you go ahead and send me that information now, I'll give you a few seconds to do that, and then we'll start class. Okay, I had a couple people that just joined. Make sure you go ahead and text me your first and last name, and make sure you write logic control in the body of the text. Give you about 10, 15 more seconds, and then we'll go ahead and get started. Okay, guys, I don't know if I mentioned this or not, can't remember, but one of the things you'll need for the class is a 3-ring binder, and you'll need a 3-hole punch. And what I would suggest you do, there's a lot of documents that I post to Canvas. It'll be a good idea if you download those documents and you put them in a 3-ring binder in the order that I place them on Canvas. For a couple things, it's a good way to keep the material organized because there's a lot of handouts, and also it's a good way to study. Now on the PowerPoints, you want to print the PowerPoints out as these note pages. If you do that, as I go through, what I tend to do is when I go through, I will, anything that's going to be on an exam or quiz or maybe something that's important that might help you out with your lab, I'll mention that, and you can write over here on the side. If you have printed out with these note pages, you can write information over to the side. It's a really, really good way to study for the class. So I recommend getting the 3-ring binder, printing out all the documents, and then printing out the PowerPoint presentations as these note pages, and just kind of take notes over to the side here. I think I mentioned on the first day that back in 2004, I got rid of the textbook, and I went to PowerPoints and just kind of spent the whole summer of 2004 rewriting the whole course, moved everything over to PowerPoint, and it's kind of been working out pretty well. So I recommend that you do that, print them out, the note pages as shown, and put them in your binder, and then we'll be good to go. So I want to talk about, last week dealt with the concept of analog quantities and digital quantities, and that was important because what we want to do is take information on the outside of the computer or PLC and move that information or data to the inside of the computer or PLC. The thing is that most quantities that we measure on the outside of the PLC, and when I refer to the outside of the computer or the outside of the PLC, the term used for that is the field, like a baseball field. So those are called field devices. Anything that exists outside the machine, the computer, is called a field device. So we either deal with the field devices outside of the PLC, or we deal with virtual devices, which are things that exist inside of the PLC. So I'll use that term, field device. And so we talked about analog and digital quantities, those quantities that we measure that are analog, and we want to bring them into the computer. What we have to first do is we have to change that analog signal into a signal that the computer or the PLC can accept, and that would be a digital signal. And so we went through digital concepts. We talked about the digital advantage, the fact that digital quantities can be copied over and over again without degrading. And another biggie is that I can take digital information and I can compress it. Those are two important things to know and to remember as we go through the course. And so what I want to do now is talk about hardware components of the PLC. And that's going to help us to understand, we understand what the PLC is composed of. It'll help us to understand programming the PLC a little bit better. So what I want you to do is to think of, and I mentioned this before, think of the PLC, your cell phone, microwaves, anything that you can program, anything that contains a microprocessor is really a computer. All computers, whether it's a cell phone, a PLC, a microwave, all computers have basic parts. All computers will have a device called a CPU central processing unit. We'll talk about that. All computers are programmable devices will contain some kind of memory. All computers will have a way to get data into the computer or into the microprocessor, and they'll have a way to get information out of the microprocessor. And there's a difference between data and information. And so we'll deal with all components, whether it's a cell phone, a laptop, a microwave, they all have those things in common. So what we want to do here is to focus on the PLC. Think of it as a computer, but think of it as a heavy-duty computer designed to work in an industrial environment. And the thing about the PLC is that if you were to walk into a factory, if you were to walk into General Motors or Procter & Gamble, if you were to walk into any kind of industrial process, you might not recognize the PLC. It might not look like a regular computer with the tower and the keyboard and the screen. It might look like a little box sitting over on the wall, or maybe a rack sitting over in the corner. You would not recognize it as a computer because basically once the PLC is programmed, you can disconnect the keyboard and you can disconnect the screen. You don't need them anymore. That PLC will continue to do its job until you need to change the program or make some kind of edit in the program, and then you connect the keyboard back up and the screen back up, and then you can program it. And once it's programmed, you can disconnect those components. And so what I want to do first here is to kind of go through and talk about an overview of the PLC, and then we'll look at some of the internal parts of the PLC. So normally, in the normal world where we actually meet face to face, I would actually bring a small PLC in. PLCs come in all sizes. They can be as small as a pack of cigarettes. They can be as large as a refrigerator. Typically, they're component built. They have different sections, or a better word would be modules. So there's modules that you can put in to expand the system to make it bigger or to make adjustments in it. And so I want to spend this first time talking about kind of an overview of the PLC, and then we'll get into some of the internals of the PLC. So normally what I would do in normal years, I would actually bring that PLC in, and I would take it apart in front of the class, and I can point to different parts of the PLC and talk about it, but we don't have that luxury because of the way we have to deliver class now. So what I did here is I made a picture of the PLC. Now I'm sharing this file. If you go to the upper, I don't know if you can see my cursor move or not, but in the upper left-hand corner, right below that little hamburger menu, there's a magnifying glass, and you can click on that, and you can make the file bigger or smaller. You can adjust that. So blow that up real big in your screen and make it so you can see the whole picture. And I want to refer to that picture. And so this is what a typical PLC looks like. As I said before, it doesn't look anything like a regular computer, but yet most of the parts in this picture, a regular computer or your cell phone will have these parts. A regular computer will have a part called a power supply. Now, the picture that you see, as I mentioned before, these are actually modules. Each one of those separate modules, there is a communication module, there's a power supply, there's a controller module, and the I/O system stands for input-output systems, but each one of those input cards and output cards are actually modules. And what I mean by modules is I can actually take one of those sections or cards, I can pull it out and replace it with another one or some other type of module. So that whole system is modular. It's the first thing to understand. Now, Just like in the picture, the PLC has a power supply. Well, your computer has a power supply. If you have a tower computer, if you were to open it up and follow the AC cord from the wall outlet into the back of the tower, it connects directly into a power supply. Your laptop has a power supply. Laptops are usually very, very skinny. They're small, and so the power supply is designed to be really small and efficient, but there's still a power supply in there. Your cell phone has a power supply. You carry your cell phone around with you, so typically the power supply is a battery. There's a battery in your cell phone. However, when the battery dies and you plug that into a cigarette lighter of a car to charge it, or you plug it into the wall outlet to charge it, then you have the same type of power supply that's in your computer or that's in any device that converts AC to DC. Again, there's a power supply. So all digital devices, all computers have a power supply, just like the one you see in the picture. Every computer has a way to get data into the computer and information out of the computer. So if I talk about a desktop computer, what are some of the ways we can enter information or data into the computer? Well, one device is the keyboard. That's an input device. Another device would be the mouse. That's an input device. If you have a touch screen, that's an input device. What about your cell phone? What are some input devices on your cell phone? Well, believe it or not, you can talk into your cell phone microphone, so the microphone on your cell phone is actually an input device. Your screen, typically on the cell phone, your screen, you can touch. If you have a touch screen, the screen is an input device. The screen is also an output device because you can get information out, you can look at it. And a lot of people don't realize it, but built inside your cell phone is a very, very small device called an antenna, and that antenna is used to transmit radio frequency and to pick up radio frequency as you use your phone. And so that antenna is both an input and output device. So my point is this: all computers, remember, a computer for us is not just a laptop or PC. A computer for us is anything that contains a microprocessor like your cell phone or a microwave. So all computers have basically the same components, and this PLC has those same components. Now it does differ a little bit in that the input-output modules here, one input device can be a keyboard, but also with the PLC, the input device can be a switch or sensor. A switch or sensors. And last week we talked about the difference between a switch, a button, and a sensor. So I can use a button as an input device for a PLC. I can use a switch as an input device for a PLC, or I can use a sensor for input devices for a PLC. Another difference is the output devices. So typically a computer, the output device might be a speaker. The output device might be the screen. Those are output devices. But a typical output device for a PLC would be like a motor, or it might be some kind of conveyor belt. It might be a light. So usually we want to turn something on or off. We want to slow something down and make something speed up. Usually some kind of machinery we're controlling for the output device. And so the power supply is common to all digital devices. The input-output system is common to all input devices or digital systems, but unique types of input devices or field devices and output devices, there's some unique ones for this thing called the PLC. Now the controller section, I think I can write on this file. The controller, this part right here, I think you guys can see that. Well, that controller, that would be like your main, the brain of the PLC, or the brain of the computer, which in digital talk is called the CPU. CPU stands for Central Processing Unit. CPU is a Central Processing Unit. And the CPU actually contains the heart of the computer, which is the microprocessor. And now in this class, we assume that the CPU and microprocessor are the same device, but really they're not. A CPU is much bigger than a microprocessor. A CPU contains a microprocessor and a couple other devices. A CPU will contain a microprocessor, a CPU will contain memory, and a CPU will contain a way to get information from the microprocessor to memory and vice versa, called a bus system, BUS, a bus. But in this class, we simplify it and we assume that the CPU and the microprocessor are one and the same device. But my point is that controller part of this PLC example would be the part that contains the CPU, the central processing unit. So as we go through the course, just kind of keep this figure in mind, this picture, and I'll refer back to it often, and just kind of maybe, I don't know, you don't have to hang it on your wall, but have it in a handy place where you can bring it up throughout the next couple of weeks, and as I said, we'll refer to it. Now, one thing that's not shown here that I want to talk about is look at the I/O section of this. Look at the I/O section. I/O stands for input output. So those are input output modules. They're input modules and they're output modules. And these, you can't really tell from the diagram, but there's actually little doors right here. These little, the part right here in front that I'm pointing to, and I'm hoping you guys can see the cursor move around here. Those doors actually open up, and if you open up those doors, what you will see is two things. You'll see columns of screws, like screw terminals, and next to each screw is a little LED light. And what you can do is connect wires to those screws. Some of you maybe install amplifiers in your car. You hook up speakers to the amplifier. You have those little clips. Those are called terminals. Well, sometimes on an amplifier or some kind of device, you connect wires. You unscrew a screw. You put the wire around the screw, and you tighten the screw down to make connection with the wire. We call that in electronics a terminal. So there's terminals behind these doors right here. And if I'm talking about an input module, what I can do is wire a switch, a button, or a sensor to that input module. If I'm talking about an output module, I can wire like a motor, or I can wire a light, whatever it is I want to control, I could wire it directly to that output module. Now that's only true if the thing I want to run is low current. It's only true if the thing I want to power is low current. What I'm saying is I can connect a low current motor directly to the output module of a PLC. Now let's say I want to control an elevator, some big heavy duty motor. I cannot connect the elevator motor directly to the output terminal of the PLC. What I have to do is use some kind of interface, and there are several interfaces we'll talk about. One we've already talked about, a relay. And you did that first homework for me where you went through, or I think that was the first quiz, where you actually went through and you understand how a relay worked. And in that video that you watched on relays, you understand that a relay basically uses a very, very tiny current and electromagnetic field to switch or control a really heavy current. I can use a really tiny switch to move a big switch back and forth. So if I want to interface, let's say, an elevator motor to the PLC, I wouldn't take the elevator motor and connect directly to the output module because that elevator motor is going to pull hundreds of amps, many, many amps. So I can't do that. But what I can do is take the coil of a relay, which is a low current circuit. I can connect that to the output terminal of the output module of the PLC because that relay coil is going to pull milliamps, thousands of amps. And I can use that relay to switch a heavy switch, which can control many, many hundreds or even thousands of amps. So I can use a very tiny current to control a large current. That's called interfacing. I can interface a large load or large motor to the PLC output, and I don't need a lot of current if I do it that way. So we'll talk more about that later on. So again, keep this picture somewhere handy where you can bring it up, look at it and refer to it, and then it'll make things a little bit more clear as we go through. One last thing before I move on to the PowerPoint that I'm going to talk about today. I mentioned the fact that both the input module and the output module, if you open up these doors, you'll see the screw terminals there. And those screw terminals, let's say you connect a button or a switch to, those screw terminals are all numbered. Now, when we talk about digital quantities or digital in general, when we number things, we start with the number 0 and not 1. That's actually quite important. So let me say that again. As humans, when we count things, we start with the number 1. So if I want to count the number of students in the room, I go 1, 2, 3, 4. Well, computers don't start with the number 1. When computers count, computers start with the number 0. So a computer wouldn't go 1, 2, 3, 4. A computer would go 0, 1, 2, 3. So keep that in mind. That'll come back at you. Well, if I open up one of the doors on, let's say, the input module or output module, I'll see on the input module these screw terminals that I referred to. But next to each screw terminal is 2 things: a LED light and a number. So it might be screw terminal 0. It wouldn't be number 1. The first one would be 0. It will be a 0, and then there would be a screw terminal you can connect the wire to, and then there will be an LED light. Well, the screw terminal number is kind of like an address, so I can refer to a particular terminal. That's called the terminal number. The screw terminal itself, as I said before, I can connect the switch to it. I can connect a sensor or a button to it. But the LED light, if I have a LED light, it lets us know if the thing connected to the screw terminal is active. And say, for example, if I have a switch connected to screw terminal 0. If I have a switch connected to screw terminal 0 on the input module, then if the switch is open, the LED light next to the screw terminal will be off. If I close the switch, the LED next to that particular terminal will be on. So I can just look at the LEDs and I can tell the status of a switch or the status of a button. So keep that in mind. And one thing about it is the software simulator that you'll use to program when we get to the labs, the simulation software, it looks just like a real PLC. It has all the screw terminals, the LED lights. So it's a very, very good piece of software to use to learn how to program PLCs. So anybody have any questions or comments over the picture or anything I said so far? Okay, well, I want to go to the first PowerPoint, which is just an overview of the PLC. So let me see if I can shrink this down. All right, so I hope you guys can see that. I don't usually share files. I like to kind of teach on the board, but with the stuff that we're talking about, at least for the first couple of weeks, there's really no good way to present it other than a PowerPoint or maybe bring an actual hardware in and point to it. So apologize for the PowerPoints, but it's the best way to present it. But the class isn't all PowerPoint. We'll do a lot of board work and programming. It's just a mixture of stuff. So I want to do an overview of the PLC, and I've been using that term PLC. If you don't know what that stands for by now, it stands for Programmable Logic Controller. Programmable Logic Controller. And all that is a heavy-duty computer designed to work in an industrial environment. What do I mean by that? Well, think about the extremes that you might undergo in an industrial environment. There's temperature extremes. Depending on where you are, it might get really, really hot. Or maybe you work in some factory where things have to cool down. It might get really, really cold. The PLC would have to withstand that. Often dirt. The PLC has to withstand dirt. Noise. And when I say noise, I don't mean audio, I mean electrical noise. So if I work in a place maybe where I'm doing a lot of welding using electrical weld systems, anytime you arc or send some kind of spark, you send off radio frequency information we call noise that could mess up devices. So PLC has to take all that into consideration. It's designed to work under harsh environmental conditions. That's the main difference between a PLC and a typical desktop computer. All right. Now this is actually pretty important, so make sure, I should have told you guys to print this out, but I didn't do it. So if you don't have the PowerPoint actually printed out, I talk about this point on this next slide. It's pretty important to understand. It's a simple idea, but I want to make sure that you remember it. It says a PLC is a solid state device designed to perform logic functions previously accomplished by electromechanical relays. So what does that mean? Well, the first thing to consider is this idea of something being solid state. What does it mean to say something is solid state. And that's actually a school or type of electronics that pre-solid state devices, we dealt with discrete components. And what I mean is, let's say you have an amplifier. Back in the old days, amplifiers were made of certain parts that they brought together and put it in a box, and they call it an amplifier. Nowadays, we can put a whole circuit, a whole amplifier on a little bitty chip called an integrated circuit. And that integrated circuit is actually a solid crystal of silicon. Now, I don't want to get into the technology too much. There's a lot of physics involved in that. But basically, a solid state device is a device that's made out of a solid crystal, and the material it's made out of is usually silicon. Well, silicon is very special. You heard of Silicon Valley or silicon devices, because so many devices depend on integrated circuits, which are composed of silicon. And so the PLC is a solid state device. It just means it contains a lot of silicon. It doesn't have any moving parts. And there are advantages to solid state devices that we'll talk about here in just a second. So the first thing to consider in this first slide, the thing you want to write down and remember, is the PLC is a solid state device. And basically that means no moving parts. And there's some other advantages we'll talk about here in a minute. The other thing about this slide, it says a solid state device designed to perform logic functions. What do you mean by that? Well, we talked about that day one, that there's three basic logic functions. There is the AND logic function, there is the OR logic function, and there's the NOT logic function. So those are the basic or the simplest logic functions we can deal with. We remember that the AND logic function basically says this, that in order to get an output, in order for a circumstance to be true, all the input conditions must be true. Or if I refer to switches, all the switches must be closed if I have a hook in an AND logic type of connection. The OR type would mean that either one switch or another or the other or both switches will need to close to have a positive or a true output. And the NOT, all that does is it takes one state and converts it to the other state. So if I start off with something on, the NOT function will turn it off. If I start off with something off, the NOT function will turn it on. So that's what I mean here in this diagram. We talk about logic functions. Those logic functions were usually performed not by switches like I showed you on the first day, because you have to have a person there. A switch requires human interaction. We want this logic to happen automatically or electronically, and so I don't use an actual switch. What they use is something called a relay, and now you guys really understand how relays work. Instead of having an actual switch that open and close that's wired in an AND or OR type logic circuit, what I can do is take the relay contacts and wire those contacts in series to make AND logic. I wire those relay contacts in parallel to make OR logic, and I can use those relay contacts to make decisions, logical decisions, and or not. And by the way, where we're headed with this is you can take those basic logic functions, those three basic functions, AND logic, OR logic, and NOT logic. You start to put them together to build more complex logical functions. And we'll talk about those. We'll get into, I think, not this week, but in about 2 weeks, we'll talk about those higher level logical functions. There's a couple of them we'll talk about. So PLC is a solid state device. It means it has no moving parts, designed to perform logic functions, the AND or NOT logic that we discussed during the first day, previously performed by electromechanical relays, performed by those relays because relays, they're electrical devices, so they don't require any human interaction, which means I can totally automate the system. So in the old days, things were controlled, devices, processes were controlled using relays hooked up in some kind of logical circuit. The PLC replaces all of that. Now, what are some of the things a PLC can do? These are just a few of the main functions or the main tasks or things that PLCs can do. There's others, but these are the main things I want to talk about here. The first one is relay switching. Now, I've already given you an example of that. We talked about in that picture of the PLC, we talked about the output module and the fact that I can take the output module, and I can connect to that a device like maybe a light to say some machine is off or on, or maybe a motor. Maybe the PLC starts a motor for a conveyor belt and stops a motor when the part is in the proper place. Well, sometimes I cannot take the motor or whatever devices I want to control and connect it directly to the PLC. So I can use the PLC, I can connect a relay to it, then I can use that PLC, I can use that relay to interface a large load like a heavy duty motor to the small current output that you would get from a PLC. Well, actually what this bullet point is referring to, relay switching, the actual output module can have solid state devices inside of the output module that behave like a relay that will allow me to switch relatively large loads. And we'll talk about the name of those devices, those solid state devices, in a later slide, I believe this week. But so in short, PLCs can basically perform the same device switching function as a relay. So I can use this solid state device that I'll name later on to control relatively large currents directly from the output terminal of the PLC. Now, not an elevator motor, but maybe something that a semi-large current. And again, I'll say more about this later. PLCs can count. They have the ability to count. So they have basic circuits made into the microprocessor that allows it to handle numbers. And one thing that they can do with numbers is it can count. Now, why would I want to count? Well, you can probably think of a lot of examples why you might want to have this computer be able to count. Why do they need to count? Well, maybe I'm trying to control, let me think here. What if somebody comes to you and they say, all right, student, I want you to design and automate a system for a parking lot. You know the arm that goes up and down on the parking lot, the gate that goes up and down? And usually there's some kind of sign that lights up that says a parking lot full, or maybe spaces available. How do you know if the parking lot is full? Or how do you know if there's space available in the parking lot? Well, the only way to do that is to count the number of cars going in. If you know the total number of spots you have, you know the total number of cars going in and out of the garage, you can keep track of if there's spaces available or if the garage is full. So the PLC that controls that in that particular situation would have to, number one, be able to count, and number two, be able to do a simple calculation, probably subtraction or addition. And so the next bullet point here shows that PLCs can also do calculating. They can add, they can subtract, they can multiply, they can divide, and depending on the machine, some PLCs can actually do high-level calculations. What about comparing? I can compare one quantity to another, or one state of something to another state. You can probably think of examples where that might be important. And then the last thing here, analog signal processing. Well, what does that mean? Analog signal processing. We already know what the term analog means. Analog means I have a signal that's continuous. And what's a signal? Well, think of a signal as a voltage or current. Either one is okay, whatever you feel comfortable visualizing. A signal is a voltage or current. Well, we mentioned on the first day of class that most of the things I want to measure and bring in to the PLC, most of those devices in the real world are going to be analog in nature. Sound is analog in nature. Light is analog in nature. Pressure, analog in nature. There are many, many quantities you want to bring into the PLC. They're all analog. And so I got to have a way of, number one, taking that analog information and changing it over to a form that the PLC or computer can understand, which is digital. So part of this analog signal processing is taking the analog signal and converting it over to digital. That's called analog to digital conversion. Analog to digital conversion. So part of that analog signal processing is that. The other part is noise. Now, I mentioned this earlier. When I say noise, I'm not talking about sound. I'm talking about electrical noise. Electrical noise. So what is electrical noise? Well, If you ever listen to the radio, and I know you guys, you probably don't listen to the radio. You probably get all information through your cell phone or your device. But back in the old days, we listened to music through a radio. And sometimes the radio, if lightning strikes, sometimes you might hear static in the radio. That's noise. Or if you're watching TV and your girlfriend or your mother, maybe she's in the kitchen and she's making a cake, she turns the mixer on, or maybe they turn the vacuum cleaner on, and you see the screen of your TV set, lines kind of it just kind of messes it up. That's the visual, that's like a visual representation of static. Again, that's noise. Basically, scientifically, noise is any undesired current or voltage that appears in the circuit. Noise comes from a lot of different places. There's natural noise when lightning strikes, or maybe something happens on the sun and there's a solar explosion. That can actually be picked up by devices, certain devices, and it's noise. Or there's man-made noise, any kind of arc or spark. Again, if I turn a motor on the vacuum cleaner, the basic way a motor works, it creates sparks on the inside of the motor. Well, those sparks, some of the energy is radiated away as a radio wave and can be picked up by electrical devices. That's noise. And in some cases, the presence of noise in an electrical system can cause things to malfunction. And so the PLC has to have a way to handle that noise situation. Imagine a PLC controlling an intercontinental ballistic missile. This PLC, the job of the PLC is to launch that missile when given a command. The command could be, I'm going to push button A, the missile launches. I don't want some guy in the next room to try to light an electronic cigarette, or somebody to turn on a vacuum cleaner and the spark causes the missile to fire accidentally. In theory, that can happen. I can have some kind of radio wave energize a circuit and cause something to misfire, or to fire when it shouldn't, a false fire. And so the system has to have a way of protecting against that. So all of that is what we mean by analog signal processing. Now, just so you know, on the quiz or exam, I expect you to understand that there's basic tasks that a PLC can perform: relay switching, counting, calculating, comparing. But I went into a lot of detail for this analog signal processing, and you don't have to go into that much detail. I'm not going to ask anything on that level. Just be aware, kind of on the surface level, that these are some of the basic tasks a PLC can perform: relay switching, counting, calculating, comparing, and analog signal processing. Pretty much all PLCs can do these basic functions, and then depending on the system you have, it may even do more. Now, remember when we said a PLC is a solid state device? And I mentioned the fact, I said, okay, we'll talk about some of the advantages and disadvantages that solid state has over the old way of doing the logic, using individual relays or individual switches. So here's some of the advantages PLCs have over relay control or relay logic. The first thing, relays have to be hardwired. I have to actually if I want to make an AND circuit with a relay, a simple 2-input AND circuit, I got to take 2 relays and I got to wire those 2 contacts together and solder those wires to the relay contacts and make sure those relay contacts are in series. A series circuit of contacts or switches gives us AND logic. So I actually have to wire that up. Well, I don't have to do that with a PLC. With a PLC, this is the cool part. With a PLC, all you do is you connect those switches to the screw terminals on the input module that we talked about, and all the wiring is done virtually. You actually literally go into the program and you draw the wire in the program. You don't have to solder anything. Those connections are all virtual. If you make a mistake in the real world, you got to desolder the circuit, clean it up, reconnect it in the right way, and resolder it. In the PLC, it's all done inside of a computer. There's no solder. And so that's a big advantage, is the fact that everything is done in software. Nothing's done with real devices. All that logic is connected in software. Smaller size. Things that are solid state are way smaller than the things that they replace. And so what do I mean by that? Well, you might realize, or hopefully unless you've been on a different planet, you'll realize that electrical things are getting smaller and smaller and smaller. Things are shrinking. As a matter of fact, there's this thing called nanotechnology. Nano is 10 to the -9. We can actually assemble things and use the building blocks can actually be atoms. We can make small machines where we use things on the scale of an atom to build these little micro machines or micro devices. So circuits are getting smaller. And the reason they're getting smaller is because, well, not the reason, but one reason is because we moved to solid state. So I can have a solid state, I can have an actual relay, or I can have a solid state relay, and the solid state relay will be orders of magnitude smaller than the physical relay. So I can make any solid state device way smaller than the physical device it replaces. Solid state devices are more reliable. Why? Why are they more reliable? Well, usually if I have some kind of mechanical thing, like a switch that moves, all mechanical things, anything that moves, there's going to be friction, and there's going to be stresses put on things that move. Any moving part eventually is going to wear out over time. We don't have that with solid state devices because there's no moving part. There's all a solid crystal, so there's nothing to wear out. So they're more reliable. By the very nature of the device, solid state devices are low power. One reason you can carry devices, not the reason, but one reason there's a lot of devices now that used to require a plug in the wall, actual AC input, that now we can use a battery for because they're solid state, and the amount of power compared to the old way, the amount of power is really, 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 really decreased. So I can now use batteries to power many, many types of devices. So all solid state devices are basically low power consumption devices. Ease of expandability. Well, what does that mean? Well, in the old way of doing things, if I wanted to change a logical circuit that was wired with relays, again, I got to get in there and actually have to disconnect wires and rewire the circuit or rewire the device. As I said before, everything, all the connections for the PLC, other than connecting the switches to the input modules and the thing you want to control to the output module, everything else is done in software. So you can expand the system, or you can contract the system by just changing software components. And the actual PLC system itself, if you go back to the picture that we referred to at the very beginning of our discussion, I mentioned the fact that most PLC systems are modular. And what that means is the control unit, the input module, the output module, those are all separate pieces that I can actually unplug from the system and plug a new one in. So the place that when you unplug a module, the thing that you would plug it into is called a slot. And so many PLCs will have extra slots where you can add other modules to it. I can make the system bigger, I can make it smaller. PLCs are expandable in many, many different ways. And then security. What do we mean by that? Well, most digital devices can be secured several ways. In the old days, if I wanted to secure switches and relays, there's only one way to do it, with the lock. I have to put a padlock on it. I got to lock it up some kind of way. Well, with PLCs, any way you can secure a computer, you can secure a PLC the same way because a PLC is a computer. So what I mean by that is, one way you secure your a computer is with a password. You can have a login. You got to have a username and the password. I can have exactly the same thing with a PLC. You know how you do that thing? I don't have a cell phone. I don't know what you call it. But you know that thing where you guys can draw on your cell phone keypad a certain shape and then it knows it's you? Or maybe you put your thumbprint on there and it knows it's you, or your retina. Anything you can do with a cell phone, in theory, you can do with the PLC for security purposes, because a PLC, like your cell phone, is nothing more than a computer. So security, there are many, many ways to secure a PLC, and that's an advantage over the old hardwired way of doing things. Now, this next slide is important. It's very, very simple, but important. Always remember this statement as we go through and you program the PLC. I mentioned that PLCs are nothing more than heavy-duty computers, but they do behave a little bit differently. See, a computer works like this. A computer, you can have a computer and you run a program, and that program is going to run until it gets to the end, and when it gets to the end, it's going to stop, or it's going to give you control. Maybe you got to do something, and it'll move to different sections of the program, and then it'll stop. Well, the PLC is an event-driven device. If you have this printed out, mark this slide. A PLC is an event-driven device. If you remember this statement, it'll make programming a PLC way easier. So here's how a PLC works. The PLC is just sitting there. It's running the program, but it's not going to do anything until something happens in the field. What do you mean by field? Remember I said there's the field, that's everything outside of the PLC, and then there's the PLC itself. That's any device or any part of the PLC. We refer to the internals as the virtual part of the PLC, or the virtual devices and field devices. Well, imagine I have a switch connected to the input module of the PLC. The PLC is on. The PLC is going to sit there and wait until some event happens. What do you mean by an event? What I mean by an event is it's going to wait for a switch to open or a switch to close. It's going to wait for a button to be pushed or unpushed or depressed. It's going to wait for a sensor to send a signal, or for the level of something's got to happen in the field, and then the PLC will react to that. And that's what we mean by event driven. Some event has to happen in the field, and when that event happens, the PLC will respond depending on how you program it, it's going to respond to that event. So PLCs don't do anything automatically like a regular computer or device. PLCs only respond to something happening in the field. A button opens or closes, a switch is moved, something has to happen. And you'll see how important it is to remember that when you actually start programming the PLC. It'll come back at you. Now, this next slide says parts of a PLC, but this is actually parts of any computer. Your cell phone, microwave, all computers have these parts. A PLC is a computer, so a PLC will have a CPU, a central processing unit. There's an I/O section. I/O stands for input-output section, a way to get data into the microprocessor, the way to get information out of the microprocessor, the I/O section. Every computer is going to have a power supply, and then there's going to be some kind of programming device. With a regular PC, it's your keyboard. With your cell phone, it's the keypad. Every device has to have a way to program it. Now, this same slide is represented with this picture. So I recommend, and I don't know about you guys, but I'm a visual learner. I like pictures. So mark this slide. Remember this picture. Matter of fact, let's talk about this briefly. So you see in the middle of this, you have the CPU, the central processing unit, and then at the very, very bottom of it, there's memory. Okay, so that's part. You can think of memory as separate from the CPU, or you can think of it as part of the CPU. Doesn't really matter. But CPUs can only work with memory, because CPUs, when it processes the data, it's got to move that data somewhere so it can be held. There's got to be memory. There's an input module that I can connect sensing devices to or switches, and there's output module that I can connect loads to, like motors, lights, whatever it is I want to control. Then all that has to be powered, so there's this power supply. So if you're a visual learner like me, this is a good way to remember the parts of the PLC. I will say that I don't remember where, but somewhere in the course, maybe on the quiz exam, I'll ask about this picture or the previous slide, so make sure you mark this slide. Here are some input devices, some typical input devices, and some typical output devices. Guys, I'm going to go over. I'm looking at the clock. I'm going to go over probably just by a couple of minutes. So if you have another class and you can't stay, go ahead and log off, and I'll record this, put it up on YouTube. You can go back and listen to it. If you can stick with me, I'll probably just maybe be about 5 minutes after the time that we're supposed to dismiss. So just want to mention that. All right, so I have these input devices, so some common input devices, push buttons, limit switches, sensors. We'll talk about these. You'll become familiar with these types of input devices. And then output devices, motors. A motor starter is a special type of relay used to, if you can't, as I mentioned, sometimes you can't take the motor and connect it directly to the PLC output terminal. Well, motor starter is a kind of interface that you can use to do that. So motor starters, solenoids, indicator lights, etc. We'll talk about these as we go through the semester, and you'll learn about different types of input and output devices. This next slide, mark this slide here. This is one I'll quiz you over on the exam. What is a virtual device? Real world devices versus virtual device. Basically, a virtual device is a mimic of a real world device. So the main one is a relay. There's an actual relay you can hold in your hand, that's hardware, but then there's software that can mimic a relay. So it's a virtual relay inside of the PLC. Every PLC has that part. Now the other two, timers and counters, a timer is exactly what you think it is. I can time how long I want something to be on. I can time how long I want something to be off. There's two types of timers. But I can have a hardware timer, or I can have this same timer as software. And then counters actually do what you think they do. They count. I can have counters that count up. I can have counters that count down, and I can have what's called an up-down counter. Those are actually mechanical types of counters that you can buy, but the PLC has the same thing as software. It has a software counter inside of most PLCs. Now the beauty of it is, if it's in software, I can have as many, just like you can open up, you know when you go into Word, you can open up Word. If you want to open up another instance of Word, you can open up Word as many times if you want to, or maybe the calculator. The calculator in Microsoft Windows. You can bring that calculator up. If you need another calculator, you just bring up another instance of the calculator. You can have 2 of them. You can have 100 of them. Well, these virtual devices are the same way. I can have virtual relay. I can have as many. I'm only limited by the size of the memory. So that's one advantage that these virtual devices have over actual devices. So virtual devices duplicate the function of relays, timers, and counters. All PLCs will have those 3. And then in some systems, some more advanced systems, there are other virtual devices that we won't consider here. Now, let's get into how PLC actually works to control some kind of industrial process. So take a second to look at this slide. Read this slide to yourself. Take a second to look at this. So back in 2004, I made all these PowerPoints, and I'm not a very good artist. But it says you have a mixer, and that mixer is used to stir a liquid when the temperature and the word "and" is highlighted. Notice that. The mixer is used to automatically stir the liquid when the temperature and pressure reach certain preset values. So you got this picture here. You got the vat, you got the tank. You got the tank. You got this fill valve over there on the left. You got a motor with this mixer. Now notice there's 2 switches inside the tank. There's a pressure switch or sensor, and there's a temperature sensor or temperature switch. At the very bottom in the lower left-hand corner, it says note the temperature and pressure switches close their respective contacts when the conditions reach their preset values. That's important to note. What they mean is those sensors or those switches are normally open switches, and they actually close their contacts when the event happens. Okay, so you got the mixer, you got these inputs, which will be the pressure switch and the temperature switch, and the way the logic works like this. when both the temperature reaches a certain point and the pressure reaches a certain point, I want the mixer to stir the liquid. Or it says also the mixer can be controlled directly from the push button. So at the bottom lower right is a manual push button. As long as I'm holding that push button, then that motor is going to turn and mix the liquid. So if you can imagine I got the pressure switch and the temperature switch. Both those have to be true. That's AND logic. So it's got to be something hooked in series. Or I can press the manual button. That's OR logic. And so what would that look like if I actually hardwired that? I actually got switches and connected the logic control circuit to control that mixer. It would look like this. I would have the pressure switch, which is right here, and I would have the temperature switch, and they got to be hooked in series. So here, now this is a control diagram called a ladder. And the way you read this is from left to right, from L1 to L2. Each one of these parts of the ladder from left to right is called a rung. I'll say more about this when I can actually show you my whiteboard. But just looking at this, if you think of current flowing from L1 across the ladder to L2, the only way for that first rung for current to go through is that the pressure switch has to be closed and the temperature switch has to be closed. The last thing in the circle, the motor coil, think of that as the thing that's going to come on when the temperature switch and the pressure switch are closed. If both temperature and pressure are true, that is, if both switches are closed, I got a path to the motor coil, that motor is going to come on. Or if I push the manual button, and notice that's in parallel with the AND circuit, that's a bypass. If I push that manual push button down, I push this push button down right here, the current can actually flow this way through the circuit to get over to the motor, and the motor comes on. So I got an AND circuit and I got an OR circuit, and this thing would function as described. Now this is an overload contact. Don't worry about that. Just ignore that. I like that's not there. Current will either flow this way if both switches are closed, or will flow this way if the manual push button is closed. That's my AND OR logic. So if you're going to actually wire this up using relays or switches, this is the way you would do it. That's hardwired logic. Well, how would I do this same function using a PLC? What would I do? Well, here you go. This represents the input module of a PLC. And notice I have these power lines, L1 and L2. This is a power line, and this is a power line. And the way to think about it is, when you read a system like this, is power always flows from left to right. Current, voltage, whatever you want to think of. But what I do here is I connect these switches. The only physical connection I got to make is wiring the actual switch to the screw terminal that we talked about earlier. So I go from power to the pressure switch to this first screw terminal, terminal number 1. Now that's actually wrong, because remember I said with digital devices we always count 0. So instead of the terminal numbers being 1, 2, 3, 4, it should really be 0, 1, 2, 3. But we'll ignore that. I got terminal number 1. I got the pressure switch connected to that. I got terminal number 2. The temperature switch is connected to that. And here's my manual push button. So all I do is wire those switches directly to those screw terminals. I don't have to hook them in series or parallel. None of the logic is done there. All the logic is done in software. But before we get to that, notice one thing. Look at this number right here. There's this number and this number. All these terminal numbers are actually what we call addresses. This is how the software is going to reference the actual physical switch. Using that addressing is extremely important. In the next slide, I think we talk a little bit about addressing. So that's important to note that. So here's what happens. You get the PLC and you connect those switches to these screw terminals. And then when you program the PLC, what you're really doing is in software, you're drawing this diagram right here. What you're seeing now on your screen is all done in software. Imagine, I think you guys are METs or maybe some of your are MEs. you use the CAD, you use CAD, and I forget the other program you guys use. I can't remember it. But you're used to doing a lot of drawing in software. Exactly what this is. This diagram, this ladder logic is drawn in software, and these represent switches or sensors. So right here, these represent in software the temperature switch and the pressure switch. And the one at the bottom represents the manual push button. This is all done in software. And what happens is you put these two switches in series, that's your AND logic, and the way you reference a particular switch is by this address here. So that's 001 in the previous slide. That 001 was like the temperature switch, I believe. And the 002, the pressure switch, I address those switches, and then I don't have to do any physical wiring. All the wiring is done in software, so if I make a mistake, I highlight it, delete it, and I change it. It's really easy to change. So this right here represents the true power of the PLC over the old hardwired way of doing things. Now guys, the rest of this, I'm out of time. I'm going to have you just read this. I mean, this to run a PLC, you'll see when you do the software, there's some steps you have to go through. So they have these cycles that go through, and you want to read these bullet points. I think I don't have to explain this. This idea of scan time is important over here. I just want to make sure you understand this, and I'll talk about this in the later slide. So read this on your own and make sure you understand the points, the bullet points. If you don't, you can ask me at the beginning of the next class, and we'll talk about it. And then the other thing here, this next slide, I never really talk about this slide, but just be aware that there's two kind of PLC software that we can talk about. There are programming tools and there's monitoring tools. Okay, so the programming tools are what we're going to use. We're going to focus on programming, and there's main programming tool is what we call ladder logic that we do in software. But there's also monitoring tools. I can have a whole, say I have a control system, maybe a conveyor, maybe it's General Motors. I can have a whole graphical representation of my system that I'm automating. So it's very advanced software you can use there. We don't go into any of that in the class, so just be aware of that. And that's the end. So guys, some of you hung in there with me. I appreciate that. If you were one of the ones that had to log off, I will put this up on Blackboard in the next couple of days. Anybody have any questions or comments?
Yeah, real quick. I was just looking at the syllabus. When you mentioned the software, it says that the edition of the book that we're going to be getting is to be announced. I was just wondering if there was if that edition had been figured out, since it says that the software comes with the book.
I think any edition will. We used, I believe it was the 4th edition. You can use any one that you can get your hands on, because the programming problems are pretty much the same. What you're going to find the 4th and the 3rd. I don't know if there's a 5th yet or not, but the 4th or the 3rd, try to find the 4th, but the 4th or the 3rd, you can use either one of those.
Gotcha. Thank you.
Hey, if you're in doubt, before you buy it, you can screenshot it and send me a picture of it, and I'll let you know if it's okay. But I'm like 99% sure that any edition you get will work for us.
Gotcha. That works. And then has this been your experience that even when people order it through Amazon, they get sent a code for the software with the book? Or is that how that works, or do they send you an email?
If it's a new, well, here's the way they used to do it. I don't know how they do it now, but when you bought the book new, there used to be a disc in the back of the book that you would use. So they probably do use a code now. If you buy a used book, if you buy the used book and it doesn't have the code or doesn't have a CD, there's another website you can go to get the software. You just download. I think it's like $40 or something like that.
Gotcha.
Hey, who am I talking to?
Oh, Will Pascal.
Okay, well, what you can do, next class, ask me about it, and I'll show you the website where all that stuff is. You can see the software and how you can download it. I'll show you where to go to look at that.
Okay, gotcha. Thank you.
Okay. Guys, have a great rest of the day. Make sure you stay safe, and I will see you on Friday.
Hey, Professor, quick question.
Yeah, go ahead.
I know on the homework you told us to write out the answers on that Word doc, but is it okay if we type the answers instead if we
Yeah.
got?
Yeah, that's better.
Okay.
Yeah.
All right.
Yeah, no, thank you.
And does it have to be PDF or can we turn it as a Word doc?
The only reason I want PDF is because if I don't have Word, whatever I'm grading it on, if I don't have Word on there, I can't open it up, but I can open up a PDF on anything.
Okay, thank you.
So you can send it in another format, but you take a chance of me not being able to grade it depending on where I am when I do my grading.
All right, I appreciate it.
All right, buddy. See you later, man. Thank you.
You're welcome.